Swayam Prabha. Digital India. Educated India.
Welcome to the lecture 22 of the course on time series modeling and forecasting. In this particular lecture, I am going to consider the periodogram analysis of a time series. The periodogram of a time series provides you an estimate of a spectral density function. If you have an observed time series, then your problem is to estimate the spectral density function of the process from which this time series has been generated. So, periodogram provides you an estimate of the spectral density function. You can also use periodogram for identifying the dominant frequencies in the observed time series. So, now before coming to the main topic, I again define the following summations. We have also used the same set of summations in the previous lecture also. So, the results have been given in equations 1, 2, 3 and 4. I am not going to repeat it. Okay. In periodogram analysis, we represent the time series y t by the finite Fourier series y t equal to a naught plus p equal to 1 to n by 2 minus 1. Then inside the bracket you have a p cos 2 pi p t by n plus b p sin 2 pi p t by n plus a n by 2 cos pi t. You know that sin pi t is always equal to 0, that is why we have not involved the sin term here. So, this model 1 is actually a finite Fourier series for a discrete time series y t. Then how many parameters are there? You have one parameter a naught here, then n by 2 minus 1 parameters a p here, then n by 2 minus 1 parameters b p here, and then one parameter a n by 2. So, in all you have n parameters. So, you have n parameters in this representation, and then you have n observations. So, n parameters to describe n observations. So, these can be fitted to the data exactly, means number of parameters is equal to the number of observations. Usually we take n as an even number, but when n is an odd number there is no problem. Then this summation runs from p equal to 1 to n minus 1 by 2. So, next problem is to obtain the parameters a naught, a p, b p and a n by 2 using your observed time series. Then for that purpose we use the method of least squares, and then we obtain the normal equations. Then for this model, how we get the normal equations? Say, what is the coefficient of a naught here? It is 1. So, you multiply the entire equation by 1 and then you take summation from t equal to 1 to n. So, on the left hand side you obtain summation y t equal to n times a naught, and then you take summation over t here. So, better if you take summation over t inside. So, summation over t cos 2 pi p t by n you get here, and summation over t sin 2 pi p t by n you get here, and then in the last term you get summation over t cos pi t. So, you get this first equation summation y t equal to a naught n plus summation over p a p summation over t, you have cos term here cos 2 pi t by n plus b p summation over t sin 2 pi p t by n plus a n by 2 summation over t cos pi t. Now, we make use of the results which I presented in the first slide. So, this summation is equal to 0, this summation is equal to 0, and this summation is also equal to 0. So, finally, you obtain a naught n. So, summation y t is equal to a naught n. Then for the next normal equation, we multiply y t by cos 2 pi p t by n, and then we take summation over t. So, on the left hand side you get summation over t y t cos p 2 pi p t by n, then you have a naught into summation over t cos 2 pi p t by n. That summation will take value 0. Then corresponding to p you have summation over t cos square 2 pi p t by n. Now, summation over t cos square 2 p t by n is actually equal to, for p equal to q not equal to n by 2, you get n by 2 here. So, you write a p n minus 2 here, and then next term you get summation over t cos 2 pi p t by n summation sin 2 pi p t by n, which is equal to 0. Then summation over t cos 2 pi p t by n cos pi t is also equal to 0. So, finally, you get for p equal to 1 to n by 2 minus 1 summation t y t cos 2 pi p t by n equal to a p n by 2. Next, you multiply both sides by sin 2 pi p t by n, and then you take summation over t. So, you get summation over t y t sin 2 pi p t by n equal to a naught summation over t sin 2 pi p t by n is 0. Now, for particular value of p, actually when you multiply this term by sin 2 pi p t by n and then you take summation over t, then it becomes 0. Now, then for the particular p, you have the summation b p summation over t sin square 2 pi p t by n, which is again n by 2, and then the summation of last term is also 0. Now, for the some other value, say for q not equal to p, when you multiply by sin 2 pi p t by n by sin 2 pi q t by n and then you take summation over t, then it is 0. So, we make use of all these results and then finally, you obtain summation t y t sin 2 pi p t by n equal to b p n by 2. And the last term you obtain, you multiply both sides by cos pi t. Cos pi t y t, and you multiply all the terms by cos pi t. Here you get cos square pi t, and then you take summation over t. So, sum of all other components becomes 0. You get, finally you obtain summation over t y t cos pi t equal to a n by 2 summation over t cos square pi t. Now, for t equal to 1 to so on, the value of cos pi t is minus to the power t. So, on the right hand side, since cos square pi t is equal to 1, so here you obtain n summation t equal to 1 to n cos square pi t is equal to 1. So, you get n here. So, you get summation t y t cos pi t equal to a n by 2 into n. Now, using these equations, you can easily obtain the values of all the coefficients a naught, a p for p equal to 1 to n by 2 minus 1, b p for all values of p, and a n by 2. So, a naught is equal to y bar, a p is equal to 2 by n summation t y t cos 2 pi p t by n for all values of p. b p is equal to 2 by n summation t y t sin 2 pi p t by n. And since cos pi t is equal to minus 1 to the power t, a n by 2 is equal to 1 by n summation over t minus 1 to the power t y t. So, from here you get the values of a naught, a p, b p and a n by 2. Now, the lowest frequency which can be fitted to one cycle or 2 pi radians per record length, that is 2 pi by n radians per sampling interval. Means you have n observations. To n observations, the maximum frequency which you can fit is 2 pi. So, per sampling interval you get frequency 2 pi by n. Then the general frequency is denoted by k cycles per record length, means 2 pi k by n radians per sampling interval. And the highest frequency which can be fitted is half cycles per sampling interval, means pi radians per sampling interval. This highest frequency is also known as the Nyquist frequency. Just to explain this last point connected with the highest frequency, for example, suppose sample is collected on daily temperature, means 24 hours interval, means maybe it is daily maximum temperature, daily minimum temperature or daily average temperature, or you may be collecting sample on a particular point of time, say temperature at say 8 a.m. Then the time series does not provide any information about the within day variation in temperature. So, if you are interested in hourly variation, how the temperature is varying from 8 hours, 8 a.m. to 9 a.m. or 9 a.m. to 10 a.m. So, if you are interested in hourly variation, then you must have collected data at least on each and every hour, means you must have hourly data. You may have half hourly data, you may have data after, you may collect data after say each and every 15 minutes or each and every minute. Then you can use that data for getting information about the periodicity in an hour, but you can't use daily data for observing the periodicity within hour. Now, for p not equal to n by 2, you can write AP cos omega pt plus BP sin omega pt equal to RP cos omega pt plus phi p, where this RP is the amplitude and this is equal to under root AP square plus BP square, and phi p is the phase of the pth harmonic, and phi p is equal to tan inverse BP upon AP. Now, you can write the total sum of squares equal to summation y t minus y bar square equal to, remember A naught is equal to y bar. So, this is equal to summation over t, summation p equal to 1 to n by 2 minus 1 A p cos omega p t plus B p sin omega p t plus A n by 2 cos pi t whole square. Now, you take a square of this. So, you get square terms means A p square cos square omega p t and B p square sin square omega p t. And when you take summation over t of these terms, you get n by 2. Summation over t cos square omega p t is equal to n by 2, summation over t sin square omega p t is n by 2. So, finally, you obtain n by 2 here, summation p equal to 1 to n by 2 minus 1 R p square, because A p square plus B p square is equal to R p square. Then at the last you have square of this term cos pi t is equal to minus 1 to the power t, but if you take a square then you get 1, you get n times A n by 2 square. Then so far as cross product terms are concerned, you get say summation t cos omega p t sin omega p t, which is equal to 0. All the cross product terms have summation over t equal to 0. So, finally, you can write the total sum of square in this form. Or if you divide both sides by n, then 1 upon n summation y t minus y bar square is equal to summation R p square by 2 plus A n by 2 square. So, basically what you have done, this is the total sum of square, and this is, you can say, the contribution of the pth harmonic. So, the total sum of square is decomposed into the contributions of different harmonic terms. Now, the plot of R p square upon 2 against omega p equal to 2 pi p by n gives a line diagram. So, if you plot R p square by 2 against omega p, then you get a line diagram. Now, Since the time series usually have continuous spectrum, it is inappropriate to plot a line diagram. So, if we assume that the time series has a continuous spectrum, although we have fitted discrete values of omega p, but the actual spectrum is a continuous. Now, in the variance R p square by 2 is the contribution of the pth harmonic in the variance of y t. So, basically what this periodogram analysis does, it decomposes the total variance into the variance contribution of different harmonics. Now, we consider R p square by 2 as the contribution to the variance in the range omega p plus minus pi by n. Remember, in omega p is equal to 2 pi p by n, and then the interval between omega p and omega p plus 1 is 2 pi by n. So, actually we consider this R p square by 2 as the contribution to the variance in this interval omega p plus minus pi by n. Then the plot, we plot a histogram with length I omega p in the range omega p plus minus pi by n, such that the area of the histogram rectangle is equal to R p square upon 2, or R p square upon 2 is equal to I omega into the total width is. So, suppose you have this point omega p, then you are considering the interval omega p plus pi by n and omega p minus pi by n. So, this interval is 2 pi by n. So, this is the height of the histogram into width, and this area, this gives you the area of the histogram, and the area is equal to R p square upon 2. Then you get I omega p equal to n R p square upon 4 pi for all p equal to 1 to n by 2 minus 1. And then for p equal to n by 2, a n by 2 square is contribution to the variance in the interval pi n minus 1 by n to pi. So, I pi is equal to n a n by 2 square divided by pi, because width of the interval is pi n by. So, we plot I omega against omega, and this plot is called the periodogram. And then for all p equal to 1 to n by 2, I omega p may be calculated directly from the data as I omega p is equal to 1 upon n by 2 summation over t y t cos 2 pi p t by n whole square plus summation over t y t sin 2 pi p t by n whole square. To verify how we get this expression 10, you just look at the expression for a and b. What is A p? 2 by n summation y t cos 2 pi p t by n, b p is this, and R p square is equal to A p square plus b p square. So, we just simply substitute the values of A p and b p in the expression for R p or R p square. So, we get this expression for I omega p, and using this expression you can easily calculate the I omega p directly using the data. Now, such analysis is called the Fourier analysis or harmonic analysis. and the overall effect of the Fourier analysis of the data is to partition the variability of the series into components of frequencies 2 pi by n, 4 pi by n and so on pi. So, basically what you have done? You have partitioned the entire variability of the data into the variability or into the variability contributed by different components of the frequencies. And once you plot the periodogram, you can check which frequencies have more contribution in the variability of the time series. So, which frequencies are dominant, have more contribution, that you can easily identify. Now, we consider the relationship between periodogram and the sample autocovariance function. We can rewrite the relation 10 for p not equal to n by 2 as I omega p is equal to 1 upon n pi. Now, here you take summation O t y t minus y bar cos omega p t square plus summation t y t minus y bar sin omega p t square. Remember that summation y bar cos omega p t is equal to y bar summation O t cos omega p t, and this summation is equal to 0. So, you get y bar. Sorry. So, this you get your last line untraceable. So, you get 0 here. Similarly, in here also summation over t y bar sin omega p t is equal to 0. And then we take square of this, you get summation over t s y t minus y bar y s minus y bar cos omega p t cos omega s t plus sin omega p t plus sin omega p s. And then this is equal to 1 upon n pi, you have summation t s y t minus y bar y s minus y bar, and then cos omega p t cos omega p s plus sin omega p t plus sin into sin omega p s is equal to cos omega p t minus s. So, you get this expression. Now, in this expression, for some of the expressions you have t equal to s. So, for t equal to s you get 1 upon n pi summation over t. For t equal to s you get cos 0 here, which is 1. So, you get y t minus y bar square. And then you have t not equal to s, or you can write as 2 times summation over t, and summation s you start from s equal to t plus 1 and go up to n, y t minus y bar y s minus y bar cos omega p t minus s. So, you get this expression. In this summation, we write s minus t equal to k. And remember that cos theta is equal to cos minus theta. So, for s minus t equal to k, the range of k is from, for s equal to t plus 1 you get k equal to 1, and for s equal to n you get k equal to n minus t. Y t minus y bar, then you have s equal to t plus k, y t plus k minus y bar cos omega p k. Then you have 1 upon n pi summation over t, this term plus 2 times k equal to, we interchange the order of summations. We take summation over k first, k equal to 1 to, and maximum it can go up to n minus 1, because t minimum value of t is 1. Then summation t equal to 1 to n minus k. K goes up to n minus t, so t goes up to n minus k. Y t minus y bar, y t plus k minus y bar cos omega p k. Now, this is summation over t, and cos omega p k does not involve t. So, you can take it outside this summation sign, and inside what you obtain, if you divide by n, 1 upon n summation over t, y t minus y bar, y t plus k minus y bar, which is equal to C k, the kth sample autocovariance. So, finally, you obtain 1 upon pi C naught plus twice k equal to 1 to n minus 1 C k cos omega p k. You can also write it as 1 upon pi summation k equal to minus n minus 1 up to n minus 1 C k cos omega p k, because you know that C minus k is equal to C k. So, this equation 11 connects the periodogram with the sample autocovariance function. So, f omega is the spectral density function when omega lies between 0 to pi. F omega is equal to 1 upon pi summation k equal to minus infinity to plus infinity gamma k C k C cos omega k, and I omega p is equal to 1 upon pi summation k equal to minus n minus 1 up to n minus 1 C k cos omega p k. Now, you compare these two expressions. Then basically what you have done, you have replaced this autocovariance function gamma k by its sample estimate C k. Of course, now the range of the summation is from minus n minus 1 to n minus 1, the entire range of the sample. So, this I omega p provides you an estimate of f omega. So, in the expression for the power spectral density function, if we replace gamma k by sample autocovariance function C k, then we get the expression for I omega p. So, this periodogram provides you a way of estimating the power spectral density function. Periodogram is a sample estimate of power spectral density function. Now, before doing the periodogram analysis of a given time series, you require some pre-processing procedures to apply to your data. The first is removal of mean. You subtract the mean from the time series. Otherwise, what happens? The periodogram will be dominated by a very large value of the first cosine coefficient, means A naught. Basically, what is A naught? A naught is your interceptor. A naught is not involved in any periodic component, or it does not have any periodicity. It is not at all connected with the periodicity. It is just the interceptor. But if you do not subtract the mean from the time series, the periodogram will be dominated by a very large value of the first cosine coefficient, means A naught. That is why you remember that before the obtaining the periodogram, we have subtracted y bar from y t. Detrending the time series. Before going for the periodogram analysis, we must fit and remove the trend from the series. And most of the softwares automatically remove the linear trend, but you must be very careful before using any software for the periodogram analysis. If the software does not remove the trend component, or if you suspect that your time series has some non-linear trend, then before proceeding further, you must remove the trend component from the time series. Then smoothing of periodogram. The set of frequencies on which periodogram distributes the variance depends on n. You remember that n is also involved in different frequencies. Omega p is equal to 2 pi p by n. So, if you have large time series, if you increase the number of observations, the set of frequencies also increases. But as n increases, the periodogram does not become smoother, but includes more spikes packed together. So, if you plot the periodogram, then it may happen that I will show you with a simulated data set also, that the periodogram is packed with a large number of spikes, or a large number of spikes packed closer together. So, in that case, you may not be able to identify the dominant frequencies. So, you must smooth the estimate by averaging value of I omega p with values at the neighboring frequencies in a frequency interval. So, smoothing is one of the options, but smoothing is not done over the time interval, it is done over the frequency interval. You select a frequency band, an interval in which you have to smooth the periodogram, and then you go ahead. Then simple moving averaging is sufficient to produce a consistent estimate of spectral density, whose variability goes to 0 and tends to infinity. So, even simple moving averaging for doing smoothing works well. Then smoothing will reduce the heights of peaks, but as long as you are able to distinguish between different peaks, it may not matter too much. But in case you do excessive smoothing, then what it does? It blurs the nearby peaks, and we won't be able to identify the dominant frequency. So, you must be very careful. If you do under smoothing, then you may find a large number of spikes packed closer to each other. So, in that case also you will not be able to identify the dominant frequencies. And if you do over smoothing, again you face the problem that it blurs the nearby peaks, and you will not be able to identify the dominant frequencies. Then one of the option is that you may consider a spectra with different amounts of smoothing and then select appropriate periodogram. Then bandwidth is a measure of the width of the frequency interval used for smoothing the periodogram. So, in fact, if you are using any software for obtaining the periodogram, then you also get the information that what is the bandwidth which the software is using for doing the smoothing, and then you can select different bandwidths and plot periodogram, and once you plot periodogram for different bandwidths, then you can choose the periodogram which is most appropriate. Average or smoothed periodogram uses L equal to 2 m plus 1 fundamental frequency values is defined as f curl omega equal to 1 upon L summation k equal to minus m to m I omega j plus k by n. So, what you have done for smoothing purpose, we have selected 2 m plus 1 fundamental frequency values, and then we average all those values to determine the value of f curl omega at point omega. Then our software uses the following formula for defining the bandwidth. Of course, here also you may find different softwares using different formula for defining the bandwidth. So, you must be very careful. So, for illustration purpose and to observe how the smoothing affects your periodogram, or how the periodogram looks like when you do not do proper smoothing, we have generated 600 observations from the model y t equal to cos 2 pi t by 16 plus 0.65 sin 2 pi t by 8 plus 0.85 cos 2 pi t by 2 plus 0.1 t. So, the process has a linear trend also, and plus u t, which is a white noise process or purely random process, and u t follows normal distribution with mean 0 and variance 1. So, we have 600 observations using this model. So, the model has terms of different periodicities as well as a linear trend, and then we have plotted the time series here, and you can easily identify the linear trend present in the time series. But just by looking at the graph of the time series, you will not be able to say much about the dominant frequencies or periodicity. So, then we have done the periodogram analysis, and this is the raw periodogram without smoothing or without much smoothing. It has very little smoothing, means this bandwidth, if you look at this bandwidth, it is too small. So, practically there is no smoothing. So, the spectrum looks like this. So, a lot of peaks packed together, and by looking at this periodogram, you will not be able to identify, or you will not be able to identify properly the dominant frequencies. So, this raw periodogram includes a large number of spikes packed close together, and you are unable to identify dominant frequencies. Then we have smoothed the periodogram. Now, this is the spectrum and this is the spectral density function. Both looks almost alike and both give same amount of information. Just for normalization purpose, you can use spectral density function if you are interested in normalized spectra, otherwise you can use spectrum. Now, you can easily identify the dominant frequencies. These three frequencies are dominant, and you notice that our original process also has three frequencies, 2 pi by 16, 2 pi by 8 and 2 pi by 2. Now, here we are using the bandwidth this much, 0.000362. So, this is the smoothed periodogram, and this provides you a proper information about the dominant frequencies, which you can't get if you do not apply smoothing. These two periodograms are also smoothed periodograms. Here I have used the bandwidth 0.00143 and here I have used the bandwidth 0.00214. Now, see what happens when you increase the bandwidth from 0.000362 to 0.00143. Then if you look at these two frequencies, they are very close to each other. Still you can distinguish between them, but these two dominant frequencies are very close to each other, almost merging with each other. And if you further increase the bandwidth, then see what happens. Now, it appears that your time series has just two dominant frequencies. So, this is the impact of over smoothing. It blurs the picture, it blurs the peaks of the periodogram. So, both under smoothing as well as over smoothing are harmful. Harmful in the sense that you get either no information, you will not be able to identify the dominant frequencies, or you get misleading information. So, that is the problem. So, the best option is you try different bandwidth and then you select the periodogram which looks most appropriate to you. Most appropriate means which clearly identifies you looking the you select the periodogram looking at which you can clearly identify the dominant frequencies. So, this is the best option. So, before ending the lecture, let me summarize the content of last 5 lectures on frequency domain analysis. The time series has 2 different approaches for the analysis purpose: time domain analysis and frequency domain analysis. Then we observed that both the approaches contain same amount of information so far as time series is concerned. So, in that way both the approaches are equal, but it depends upon your application which approach you should prefer, whether you are more interested in identifying the dominant frequencies or you are more interested in identifying the lagged observations which are more prominent in the variability of the current observation y t. So, it depends upon your application. Periodogram analysis, which I covered in today's lecture, is a way for estimating the spectral density function, but while applying the periodogram analysis, you must be very careful before smoothing it. If you do over smoothing, then it blurs the picture, means it blurs the frequencies. You won't be able to identify dominant frequencies. If you don't do the smoothing, or if you do a very little smoothing, then again you get a lot of peaks, and again you won't be able to identify the dominant frequencies properly. So, you must be very careful. So, this is where I am going to stop. Thank you.
Hello everybody, welcome back, and here I am to give a preview, very short obviously, in the area of what we mean by operation research and optimizations. So, we know operation research and optimization is used generally where you have some resources and you want to utilize them in the best possible way considering what your main objective is. Now, if we stop here and go back in the past, so the obvious question comes, from where did this technique of operation research and optimization, which is an area of mathematical techniques, come into the existence. So, generally, even though the work has started from areas of mathematics, economics, but generally it is considered that operation research and optimizations were very heavily used, and it became popular during World War II in trying to schedule different resources, manpower, armaments, considering there were resource constraints, time constraints and space constraints and so on and so forth. Now, for the general public, it should be aware that we consider from the academic point of view, there are different people, very famous people who have worked, but George Danzig is considered the father who really proposed the technique of linear programming as a very nice tool where you can use operation research techniques in order to optimize the resources which are there depending on different constraints which you have. And after that, things have really moved very fast. They have been developing throughout the world, they have been usage, they are different type of societies, so on and so forth. And in course of time we see, and we still find exciting areas of application, but theoretically there has been a growth in techniques like robust optimization, stochastic optimization, dynamic programming, parametric programming, nonlinear programming, so on and so forth, and they are used depending on the concept and the areas of application which we see for either finance, for marketing, for scheduling, for engineering field and so on and so forth. Now, application of OR and optimization, if somebody asks, is a very difficult question to answer, because if I start now, it will almost take about 1 hour to give you all the areas of application of optimization and operation research are. But to keep it very brief, considering that you are all ready and eager to take that as a subject, I will just highlight the areas of applications, some of which are in scheduling, in assignment problem, in facility location, like you want to build up a factory, you want to build up some storehouse, so on and so forth. It is used in network flows, like you want to transport some goods, transport manpower from one area to another area. So, how we will try to basically do it in the best possible way. What is best would obviously depend on how you are trying to use optimization as a tool in different areas. It can be used, operation research and optimization can be used in health services, in financial portfolio management, asset liability management, game theory and so on and so forth. Now, in the recent past, even though it is very well known, but still I would like to highlight the point that the computing powers and the techniques of operation research and obviously in statistics has exponentially grown. And with very sophisticated programming being available, like we know that there is MATLAB, there is R, there is SAS, which are different type of optimization tools. We see nowadays that operation research and optimization is also used in health sciences, in gene replication theory, in area of say for example prediction of weather, in the area of say for example prediction of earthquake, how you find out the best possible way to take actions such that it meets your overall demand. Say for example in prediction of earthquakes, you would like to basically build up your houses, build up the dams, build up the overall locations of people staying in different localities in such a way that the minimization of the losses are sustained. Furthermore, after the advent of computing and advent of different techniques, we see many meta heuristic and heuristic techniques are very heavily used in parlance of operation research and optimization by joining them together such that you get the best benefit. So, if the question arises what are the meta heuristic techniques, I would again be very brief, because again there is a huge amount of literature, huge amount of application areas, huge amount of research which are being done in the area of genetic algorithm, taboo search, ant colony optimization, simulated annealing, then in the area of particle swarm optimization, in the area of artificial immune system and so on and so forth. In the coming years, it is thought and definitely with some positive viewpoint that the area of multi-criteria decision making and multi-objective programming, where you use different type of tools and use the different advancement of optimization which has been made in such a way that you can basically optimize two different objective functions which are there in front of you, such that either if considering the area of finance, you can either maximize your return for the portfolio or minimize the risk also, or say for example you want to basically have a layout such that minimization of cost is one factor and the maximization of say for example benefit which accrues to different type of users in this overall layout can be attained at the same time. So, obviously it means that what we are seeing is a huge application of optimization along with different type of computing and heuristic techniques, such that in years to come this area of optimization would become one of the best tools where you accrue and get the benefits in the best possible way. And I am sure that the students or the participants who will take this course will find it an exciting add-on to their CVs and to their curriculum vitae, such that they can understand the techniques, how they can be used in the best possible practical sense. Thank you.